Modern entertainment over the last century has been heavily dependent on the recording of sound. Sound that could be speech, music, natural sounds, or sound effects. Microphones are needed to record most of these sounds, but there are other tools that can be used to shape the sound during and after recording. One of these is EQ, or equalization, which can be used to emphasize or reduce some of the harmonic content. We have these on our stereos in the form of changing the bass or treble. Another important tool is a compressor. A simple explanation of what a compressor does is that it limits the dynamic range of an audio recording. This dynamic range is the difference between the loudest and quietest parts, and a compressor would make this difference smaller. For example, in a dramatic movie, a character might have a monologue where they start off speaking at a low volume and then end up yelling at a high volume. The actor's naturally dynamic range might cause the recording to distort when the volume is too high, and the quieter parts might need to be louder in the final movie. Used during recording, a compressor could decrease the loud parts, which would allow for the overall average volume to be raised, and therefore help to bring up in volume the quieter parts. So in this video, we'll take a look at some of the parameters of a typical compressor and understand the mathematics behind some of them. We'll also take a look at how compressors have come to be used as an effect in a lot of modern music through sidechain compression. The first parameter we'll start with is threshold. This is the simplest parameter on a compressor, as threshold sets a volume level for when the compression will occur. The level is a measurement of decibels, and when a sound reaches the set decibel level, then the compressor will start its job of changing the resulting output level. Next is attack. Once the threshold has been crossed and the compressor starts its job, there is a way to control how much time it takes to lower the volume. This time can be set by the attack parameter. The times can be very fast, measured in microseconds, which are 1/1,000,000th of a second, or they can be longer, measured in milliseconds, which are 1/1000th of a second. In another video, we discussed the envelope function on a synthesizer, which also has an attack parameter. Attack on a compressor works in the same way. Once the compressor is triggered, its job is to lower the volume of the sound source. If the attack is set to 0, then the volume would be lowered immediately. If the attack is set to another time other than 0, then it would take that much time to reach the lower volume. So the next question raised by the discussion on attack is, what will that lower volume be? This is set by the next parameter, ratio. This is one of the most obvious applications of mathematics on a compressor. The options to choose from are set ratios, like 1:1, 2:1, 5:1, etc. In general, if the ratio is x:1, then for every 1 decibel that a sound is above the set threshold, then the volume will be reduced by x decibels. For example, if a sound source is 5 decibels above the threshold and the ratio is set to 2:1, then the volume will be lowered by 2 times 5 or 10 decibels. At this point, let's listen to these parameters so far. I'm going to play a piano sound by just playing a note a few times in a row. The loudest part of the note is the initial starting point, which is a loud noise when the hammer strikes the string. We call the initial starting point the transient. This is followed very quickly by the vibration of the string, which dies out over time. With no compression, we can see on the screen that the loudest the piano sound gets is from this transient, and it is at a level of -11.8 decibels. I have the compressor threshold set to -30 decibels, the ratio set to 2:1, and the attack time set to 0. As I play the piano back, I'll change the attack time so we can hear the lowering of the volume by the compressor come in later after the transient has passed. Keep an eye on the graph of the white line at the top that shows the volume lowering. You can also notice the level of the transient is lower than -11.8 decibels while the compressor is working, even as I increase the attack time. We might have noticed some distortion when the attack time was set to 0. This is because the compressor has to act very fast to lower the volume, and that distorts the incoming sound wave. When the attack is set to a time greater than 0, then we hear the initial transient of the piano sound before the volume is lowered. When this happened in the video, the white line showing the lowered volume did not have as large of a dip as when the attack time was 0. One thing to point out from this demonstration, after the compressor does its job of lowering the volume, it then returns the volume to where it was initially. This return is called release. The parameter is also a measurement of time, just like the attack parameter on the compressor, and also just like the release parameter on a synthesizer. Options for release time are usually longer than those for attack time, and typically release times are measured in milliseconds or seconds. For the piano demonstration, the release time was 1000 milliseconds, or 1 second. Finally, with the compressor doing its job of lowering the volume of the louder sounds, we can use the makeup parameter to bring up the average volume of the sound source. Since the louder sounds are made quieter, this helps to increase the volume of the quieter sounds. Used on a piano, this can help to make the quieter articulation of a performance be more present when mixed with other instruments. And this leads us to a final discussion about one use of a compressor: sidechain compression. This could almost be described as an overuse of a compressor, but it is an interesting use with some application of mathematics. When using sidechain compression, the compressor will affect the volume of a sound source, but it will be triggered by another sound source. In this next example, I will have a constant sound from a synthesizer, and I will have its volume be changed dramatically by a kick drum. Here are the two playing together without the compressor on. And now here it is with the compressor on the synthesizer. And now I've muted the kick drum, so you are just hearing the synthesizer with the sidechain compressor effect. Using some simple mathematics, I've added a rhythm to an otherwise constant sound. The tempo is set to 80 beats per minute, with the kick drum being played on each beat. This means there is one kick drum sounding every 0.75 seconds, or 750 milliseconds. I have set the release time to 750 milliseconds, and this gives a pulsing rhythm to the synthesizer that is in tempo with the song, where the volume dips dramatically and then fades back in before the next beat. You can hear sidechain compression in a lot of popular music. Here is one example.